Hello everyone, welcome back. Then we will focus on the variables. Okay? The state, at first write down the state of a system. The state of a system. The state of a system, for example, we are taking the example of any gaseous system. As you have learned before, Boyle's law, Charles' law in your class 10. So a state of a system, how to express in which state the gas is. So we need some variables, for example, number of moles, then pressure, then temperature, then volume, right? So here we will generalize, because in this chapter we have learned that we will generalize some physical chemistry problem. So we will generalize all these variables. So make a heading of variables. We will generalize with respect to the dependency on, we will with respect to the dependency on matter or mass. All the variables which will depend on mass and which will not. Clear? So with respect to that, we will divide the variables into two types. One will be our extensive variable, and you can apply this concept, that is extensive variable and intensive variable, not only in thermodynamics but also uh, if it is required in any physical chemistry problem. Okay, intensive variable. So extensive variable, they will be mass dependent. Okay, so first example will be mass, second will be volume, right? Mass, volume. And for intensive variable, they are mass independent. So NPTV, which one will be mass dependent, which one will be extensive, and which one will be intensive property? If we make a list, then pressure will be our intensive property. Pressure will be our intensive property. Why? Because pressure means force by area. Okay, if you divide force, if we can't understand, of course area is, this area is mass dependent. So here I am listing area as extensive property. Clear? Because more the area, more the mass, this. Now if you can understand force, so we will divide force as m into a, mass into acceleration, and of course area means, this L square. If we are writing, then this is mass dependent force, because the equation of force, it is mass is present, so it is mass dependent, that means it is extensive property. And this is also extensive property. So the ratio of two extensive properties will be intensive property. So pressure is intensive. Clear? Now temperature. For example, when we are considering, or when we are doing any chemical reaction, most of the time we check the pressure, temperature, so the temperature, when we are considering the temperature, that means the temperature of this room. So we will not take the thermometer and we will check each and every corner of this room, right? So for example, a gas jar is provided, so the temperature of the entire gas jar, the gas particles are moving, so the temperature, if we are also changing the temperature, so after some times, again when you will stop changing, you will stop giving the heat, the temperature will be same for the entire gas chamber. So the temperature is also intensive property. Okay, Now volume we have listed here as extensive property. Now tell me what will be number of moles. Number of moles, it is extensive or intensive property. If we are taking 2 mole nitrogen, if you are taking 1 mole nitrogen, 1 mole nitrogen, 1 mole nitrogen means 14 into 2, 28 gram, right? If you are taking 3 mole nitrogen, so of course it will be greater than 1 mole nitrogen. So mole is also extensive property. Clear? So you have to make a list where you can classify between the extensive and intensive property. Some of the question you can see they are asking about the intensive and extensive property. Okay, so some other extensive property will be, if we are listing, so for example energy. Okay, now if we are writing molar energy, we are using the term molar, that means we are fixing the amount, the mass, so it will be our intensive. Now enthalpy and molar enthalpy. Enthalpy, what is enthalpy? Enthalpy is also a energy term. It is a one type of energy. We will study later about enthalpy. Now internal energy. So any form of energy, if it is not mentioned as molar, internal energy is also extensive property. Now if we are writing molar internal energy, so it will be intensive property because we are fixing the amount. Okay, so volume, as we have written, extensive, but if just don't take only volume, just take the entire variables given. If it is written molar volume, so of course it is intensive because you are fixing the amount. Okay, now volume we have written, if it is written molar volume, so of course it is intensive, as we have explained here. Density is also intensive property. Now concentration, intensive. Concentration, for example, you are cooking something, cooking soup, and you are checking if we have to add more sugar, more salt or not. Then what we do, we'll take a spoon of it and we check it, and then accordingly we will add, right? So you're not drinking or not eating the entire soup, and then we are deciding, no, the salt was less or more. So we are taking from a beaker from a beaker of soup, we are taking only 1 spoon of it. That means concentration will be our intensive property. Okay, now mole fraction. Mole fraction will be our intensive property. Refractive index, yes, it is our intensive property. Specific heat, only heat is extensive. Okay, heat is extensive, but specific heat, we are in the unit of specific heat, you could find the unit of mass also. That means we are specifying the amount, so again it is intensive. So the main keywords is, if you are specifying the the amount, then it will be intensive, otherwise it will be extensive property. Clear? Clear everyone? Now we will consider different thermodynamic process. Different thermodynamic process. Okay, before that it will be easier if we consider one more thing, one more classification of variables. Again we are classifying the variables, but before that we have classified according to the dependency on matter or mass, right? Dependency on matter or mass. But now this time we will consider, or we will divide or classify the variables according to the dependency of path. Path means we are changing the state. For example, we are expanding the volume of any gas. Okay, so we are changing the state, so we are following one particular path. For because this thermodynamics we are learning with respect to the chemical system, so I am giving example of the chemical system where we can actually apply, right? So according to the dependency of path, that means in which way we are proceeding. Clear? So two paths means one will be initial state, and one will be the final state. That means from where we are converting. Clear? So example will be, for example, we are converting the temperature, we are increasing the temperature from 30 degrees centigrade to, we are, for example, 70 degrees centigrade. So we are changing. So in initial state the temperature value, so T1 was 30 degree and T2 will be 70 degree. Okay, another example you can give, for example, the expansion of volume. So before the volume was 3 liter and after expansion it will be 5 liter. So different process we will do. So the variables which will depend on the path, they will termed as so we are changing. Now one more thing, we are going from initial state to final state. So various process, various pathway we can use. So in between there will be one term which is path. Okay, so we are calculating, we are not calculating, we are telling that the variables, we are classifying the variables which will depend on this pathways and which will not. Okay, so at first the variables which will not depend on the pathways, they will be termed as state function. Okay, they will be termed as state function. And examples of the variables, keep it in your mind that energy and heat, they are the very two common examples which are path dependent variable. So they are not a state function, they are path dependent variable. Okay, so they are not a state function, So which will be our state functions? There are various examples of state function: pressure, volume, temperature, enthalpy, H, entropy, S, Gibbs free energy, G. Okay, so various example is given. And internal energy, which often described as U or E in different books. So they are all state function. Don't get confused with state function and intensive extensive property. They are the two different things. When we are classifying the variables with respect to the dependency on matter, then two parts is extensive intensive. But when we are classifying the variables with respect to the path, For example, you are changing, so the variables, the values, it will also change, right? But the change, sometimes it will depends on the path, sometimes it is not. When it is not dependent on the pathways, then they are termed as state function. State function. So very important thing, for the state function, they only depends on the initial and final state. They only depends on the initial and final state. Okay. So for example, you are studying, the expectations of your relatives or of your family members are this, that you will get 90% above score. Okay, that is their expectation. So their expectation is the state variables, state function. Why? Because they will not understand in which pathways you are doing this, transformation. You have to do. So their expectation is somewhat state function. So for example, before the exam you got various illness, and you can't give your exam properly, so they will not hurt anything, right? They will only focus on your result, your marks. So their expectation is one type of state function. Clear? Now in thermodynamic system, when we will do some numericals problem, then it will be more clear. So the state functions only depends on the initial and final state. Clear? Now focus on different types of thermodynamic process. Okay, different thermodynamic processes. First one will be isothermic process. You have already done this. Isothermic means, again we are I am taking example of any gaseous system, right? So isothermic or isotherm, a graph name isotherm, you have already learned this. If I draw pressure and volume, so it is isotherm because the graph looks like hyperbolic nature of this curve, right? Pressure and volume where we got this equation, P inversely varies with volume when temperature is equal to constant, right? The gas laws, the name of the gas laws is which one? Charles law or Boyle's law? Exactly, you are right if you are thinking about Boyle's law, right? So it is PV isotherm where the temperature is fixed. So the graph look like this. Second one, so if it is isotherm, okay, now the state function was temperature was the state function. So it will depend only on the initial and final state, right? So isotherm, that is we are not changing. T1 is also T and T2 is also T. So we are not changing. So delta T will be T2 minus T1 which is T minus T equals to 0. So in short, delta T equals to 0 or T equals to constant for isothermal process. I'm making it isothermal, okay? Isothermal process. Second one, isobaric process. Can you guess which variables we will keep constant? Bar is unit of pressure, right? So you have guessed it right, pressure will be constant. So P1 is also P, P2 is also P. So delta P will be 0 similarly. Okay, so P equals to constant. So the curve will look like pressure and volume curve if we are drawing. So it will look like So this size represents pressure, this size volume. So pressure volume curve, pressure is constant. So you are taking a particular pressure, pressure is constant. So it will look like this, right? Isobaric process. Then third one will isochoric process. Isochoric process. Okay. So very common variables, that is volume, we will take it as fixed. V1 is equal to V, V2 is equal to V. So delta V equals to V2 minus V1, which is again 0. So when volume is constant, clear, then the curve will look like, if you keep volume constant, that means under same volume, so we are fixing one exact value of the volume, so it will look like this. Okay, now this is easy. Because why they are 0? Because temperature, pressure, and because temperature, pressure, volume, they are all state function, and state function only depends on the initial and final state, right? So if they are fixed, their values are fixed, so in different process we have taken delta of that exact variable as 0. Now fourth one, as the most important one, is our adiabatic process. Okay, adiabatic process. Now in adiabatic process, remember that Q equals to 0. If you are taking Q, some of the books, Q is considered as change of heat. But in your understanding, for better understanding, you may take delta Q equals to 0. Delta Q is also representing change of heat. Delta means the change. So small q doesn't mean that heat is equals to 0. No, the change of heat equals to 0. Remember that. If it is only q is written, no delta sign is given, so under it you have to write down the change of heat. You are taking it as q or delta q. Clear? That will be 0. So for adiabatic process, I will compare this curve with the isothermal process. Okay, then we'll understand it better. So if it is the isothermal process, okay, that will be our adiabatic process. Okay, if you are starting from a same point, then if it is a if it is a adiabatic process, this one. So which one is adiabatic process? Which one? This one is adiabatic process. This one is isothermal process. Remember that there will be no exchange of heat between the system and the surroundings for adiabatic process. So change of heat, which if we have taken it as q or delta q, which will be 0. So the slope of adiabatic and isothermal process, if we are taking the slope of adiabatic process, the slope we are taking at m of a, and the slope we are taking at m of I. So tell me which slope is greater. Of course it is falling. For adiabatic process it is falling drastically, right? So the slope will also be greater. So we can write ma is greater than mi. Clear? So how to represent all the process in a single graph? Let's draw it. Okay, the pressure and volume change we have taken. Now for, at first we are drawing for isothermal. Okay, if it is isothermal, then we are doing it for adiabatic process. Then again we are doing it for, this one will be isobaric process, right? And let's use another color. This one will be for isochoric process. So let's write down. This is will be isochoric. This one will be isobaric, and this one will be isothermal, and this one will be adiabatic process. Clear? In one graph, if we have to explain or if we have to remember, so that will be our entire graphical representation. Clear, everyone? Okay. Now the fifth one, which is very easy also. The fifth one, yes, we left one, that is cyclic process. Simple. Cyclic process, we are changing pressure and volume. So I am drawing this A, B, C, D. This is also cyclic process because we are starting from A and again we are returning at the point A. So all the state function will be 0. So delta T value will be 0 for the entire, cyclic process means entire process. If we are calculating, delta T will be 0 and all the state function. So I am writing in short, that is delta of state function will be 0. And here one extra information for isothermal process. Remember that internal energy, if delta T equals to 0, then internal energy will also be 0. Just for now, remember the equation, that is delta U equals to N CV delta T. N is number of moles, CV means specific heat capacity, and delta T. So clearly if delta T is 0, that means delta U 0. So remember that for isothermal process, if you have to calculate what will be the change in internal energy, so clearly it will be 0. Okay. So these were the different process of thermodynamic. These were the different thermodynamic processes. Thank you.